So we are welcome to the class today. So as we can see on the screen, we are going to look at under our clarification series, important clarification series. We are looking at the important facts and points to note about support vector machines. Support vector machine is one of the very popular and very powerful machine learning algorithm. And from experiences of many people in the literature, and also my own personal experience and some of my teams, it's a very unique algorithm to use, especially in areas where the data set is not much, when you have few data samples, because we have discussed the concept of cost of dimensionality. The more the number of features you have, the more the number of samples you need to get reasonable results. And unfortunately, as the number of features increases, the growth function is exponential for the number of samples needed. And you know that exponential growth is something you cannot really meet up with. So for example, if you have like one feature, maybe you need like 10 samples to make something reasonable. With two features, it doesn't become 12 samples or 13, it becomes 10 raised to the power 2. That is 100. When you have three features, it becomes 10 raised to the power 3. So the growth is exponential. So you have x1, you need 10 raised to the power 1 number of samples. With x1, x2, then you need 10 raised to the power 2, and keep growing like that. So anything that grows exponentially is difficult for you to meet up with that growth. So, and that's why we add the concept of cost of dimensionality, which is a very big problem that machine learning algorithms do face. However, support vector machine, which is relatively new, not new just like yesterday, but compared to neural network and also for others, we consider a relatively new classification method for both linear and non-linear data. See, it's capable of solving both linear cases and non-linear cases, and I'm going to explain what we mean by linear and non-linear cases shortly. It's usually very, very powerful. Like I said, from experiences, my personal one and my team, in maybe areas where data sets are really very difficult to come by, like in material sciences, that you have to carry out a lot of experiments in the laboratory before you can get the data set. So, and even some other medical data sets also are not really available. We've noticed that support vector machine has a unique capability to still perform in the face of this kind of a system. And also when the data set, the dimensionality is really high, it has a unique way of still scaling through despite this. So what is responsible? So we want to clarify a couple of points about the support vector machine based on repeated requests from members and acquaintances that, okay, they will have some they want some clarification of SVM. Why is it unique? And why does it seem to solve problems uniquely where other algorithms might not be able to solve it? However, we are not saying support vector machine is the best, because I mentioned this earlier. When you say a particular algorithm is the best, it means you don't understand the way machine learning works. There's no algorithm that is best, but then you can have one or few of them that can maybe work for you in several cases. I've used support vector machine unsuccessfully in few cases, whereas even the one we call lazy classifiers like k-nearest neighbor perform excellently well, and SVM was not able to perform. So that is confirming the fact that what I usually tell us, that let the data speak. This is the basic concept we must always remember. Let the data speak. It depends on the data you are faced with. A system an algorithm can work for many data sets. It might fail on a particular data set. That doesn't mean it's not good. But support vector has some background, unique theoretical basis, and a working pattern that makes it to actually be very, very unique compared to others, which is what we want to clarify for ourselves in maybe next few engagement, maybe 2 to 3 weeks, hopefully. Now, starting with, we said that it can cater for both linear and nonlinear data. It uses a nonlinear mapping to transform the original training data into a higher dimension. This is one of the unique secret behind SVM. That's a way of believe that if a system is not separable or is not separable at a particular lower dimension, it can push it to higher dimension, at which point it becomes separable. And we are going to give practical example to demonstrate this, how it works. You see, in real life, at a very normal scene, something might not be separable. A problem might not be separable. But when we subject it to a particular physical phenomenon or a particular system, it might actually force it to become separable. Separable means, are we able to draw a line? Because support vector machine is one of the class of discriminative classifier. Discriminative classifier. Discriminative classifier. That is, it always tries to draw a line. You believe you can always draw a line to separate two classes. And it only works on two classes also. Support vector machine only work on two classes at a go. And that's why later on also, we are going to talk about how do you deal with multi-class problem with SVM? Because it has only the capability of working on two classes at a time, since it only has the power of drawing a line between two classes. So I have class A, I have class B, this is class B, these are A with dot, dot, dot. Can I draw a line between them? SVM works in this pattern. So if I have three classes, for sure, you cannot draw a single line between three classes. It's not workable. You can only draw a separate line between two classes. So how does it solve more than two classes problem, like three classes or more? So we're going to talk about that one also later on, inshallah. Now, moving further. So now, that it's always used the non-linear mapping to transform the original training data into a higher dimension, because of the belief that at higher dimension, everybody will sort itself out. So with the new dimension, it searches for the linear optimal separating hyperplane. That is the decision boundary. So once it gets to new dimension, maybe at the lower dimension, this thing is not separable. When we push it to higher dimension, it becomes separable. This is a natural phenomenon that we do face every day. So with an appropriate nonlinear mapping to a sufficiently high dimension, data from two classes can always be separated by a hyperplane. So you can see we always mention two classes because SVM only works for two classes. So when you have more than two classes, then you need to build multiple SVMs, either one against all or one against one. We're going to do that later on. So then it moves further to now, SVM now find the hyperplane using support vectors, which is essential training tuples, and then the margins defined by the support vectors to separate the data once the training is actually done. Now, these are a couple of, there's very important question we're going to answer, but at this level, it might look superficial. So let's go over those questions and the reality. Why is SVM unique and effective, especially on high dimensional data? See, when the dimension of the data is very high, there's a uniqueness of SVM because of the ability to take just few samples, which we call support vectors. That's where the name actually came from, support vectors. It uses support vectors to represent the entire data sample. Even when you have millions of samples for your training, after the training can take a lot of time. You are going to see later. SVM is one of the systems that depend on the very strong mathematical background. Quadratic equation, optimization problem need to be solved. But once you take your time to do the training, it will identify few support vectors as the representative values for the entire data set for your training. It means you don't need to refer back to all the huge training data. Just know the support vectors. You are good to go to do new classification for unseen data. As we know that when you train, the essence of the training is to get ready to be able to identify the new samples that are going to come later on. Now, we say this, the complexity of trained classifier is characterized by the number of support vectors rather than the dimensionality of the data. So once you finish the training, then support vector will represent the entire system. So we can as well just forget about the training data we use now, since we have used the training data to identify the support vectors. And these are going to be the representative value. So the support vectors are the essential or critical training examples because they lie close to the decision boundary. Once the decision boundary for support vector machine is established, those points lying closest to that particular decision boundary are referred to as support vector. So we pick them, we take note of them, we can discuss the other samples, other training sets. These support vectors, they are enough for us to do classification for new samples during the testing, the validation stage. We say if all other training examples are removed and the training is repeated, the same separating hyperplane will be found. Can you see that? Once you identify the support vectors, if you repeat the training now using the support vector, then you are still going to get the same hyperplane because those are the unique training examples that have been identified after the initial training process. So we also say that the number of support vectors found can be used to compute an upper bound on the expected error rate of the SVM classifier, which is independent of the data dimensionality. And finally, we said the SVM with a small number of support vectors can have good generalization, even when the dimensionality of the data is high. So you can have millions of data samples during the training. However, the few that are very close to the support vector, to the boundary will be selected as the support vector. This is just to quickly show you a visualization of the support vectors. Let's look at this case now. See, these are two classes, class A, this class B. You can see after drawing the separating hyperplane, we talk about how do we draw the hyperplane, how do we select the best hyperplane. We'll come back to that one later on. You can see here, this is the support vector here, this support vector, while this is the support vector for this side. You can see here, for this another example, here you have three support vector here, or two. Those ones that are touching the line directly, they are the support vectors. Those that are not touching them, they are not the support vector. So we're going to select this 1, 2, and 3, and we can discard the others. These are the most important training samples after training our support vector machine. So these support vectors will continuously be referred to during our validation, our testing, because they play a huge role. However, if you select the wrong support vectors, then you end up having wrong results. That is why when we're drawing the separating hyperplane, it's very, very important that we draw the better one and the most important hyperplane. And we're going to discuss this. How do we select the correct hyperplane, as the case may be? Now, let's look at a little bit of history of SVM. We say Vapnik and his colleagues, so in 1982. So when we talk of 1982 with machine learning, we can see it's relatively new. They made a groundwork work from the Vapnik statistical learning theory. The idea of statistical learning theory came up in the 1960s. However, Vapnik and colleagues were able to bring this particular kind of unique theory to act on support vector machine in the 1990s. The features of it include the training can be slow. However, accuracy is high due to the ability to model complex nonlinear decision boundaries, which we call margin maximization. The training said the training time could take time in SVM. Yeah, it's confirmed. This is one of the stuff we have seen. But once we have finished the training, because of this, the uniqueness of support vectors, once you spend your time doing the training and you select the support vectors, then the testing becomes very fast because you are not going to use the entire training set for the testing or validation. The support vectors are what you are going to be using. for the subsequent classification. So the testing or real-life deployment is going to become faster once the training has been done. So support vector machines support both classification and numerical prediction. That is the one we call regression. However, initially it was meant to solve classification problem, but later it was extended to cover regression capability. So application of support vector machine ranges from handwritten digit recognition to object recognition, speaker identification, benchmarking time series, and a host of other applications. Personally, me and my team, we've used it a lot on our materials science-related applications, because here we found out that we have relatively many features with very few samples. Sometimes samples that as few as 26, 20 samples, even 16 samples sometimes. Support vector machine still somehow find a way of being able to model it with acceptable results, where all other algorithms we use have failed. Neural network will not survive sub few samples. To use neural network successfully, you need appreciable number of samples. But for support vector machine, we found out that even with very few samples, it performed excellently well, where other methods will have failed. Now, so we say support vector machine is a technique used for classification, regression, and even outlier detection. Yeah. Also, it could be used for outlier detection under the missing value treatment. So an outlier treatment method, we mentioned that we can use actually another machine learning algorithm to actually establish, to check if there's an outlier or not. So because support vector machine has an unsupervised learning version, which is known as support vector clustering. So it can cluster the data together, and then you can be able to do those ones that are not belonging. For example, you give me a data set that belongs to 2 classes. I can decide to ask support vector clustering to cluster into 3. I know these are supposed to be 2 classes, but I want it to cluster into 3. After the clustering, maybe I now have 3 classes. One is having 500 samples, another one is having 450 samples, and then another one is having 50 samples. I can deduce that these 15 samples are likely to be dirty data, noisy data, or outlier. So I can kick them out of my sample. So now I'm now left with 950 samples to be used for training and testing. Sometimes we do this to be able to make sure we are working with good data set. You do a kind of clustering before you start your main. That is, if you are facing challenge, always let the data speak. Before you assume your data is noisy, can you run the experiment first and see what you are getting? Let the data speak. It is when your data is not able to land you reasonable result, then you start thinking of, oh, what can we do? Maybe this data is noisy. Can we do some clustering before we actually do the training and testing? This is the procedure we discussed earlier on in one of our earlier videos. You can check it out. The procedure, how to decide when to do pre-processing and how much of pre-processing is enough. So these are very important techniques that we need to master and pay attention to whenever we are building machine learning models. Now, so SVM has the support vector clustering capability. So once done, the new example that are then mapped into the same space can then be categorized based on which side of the gap they fall. Like I told you, you have your data, you draw a line, there's going to be support vector touching this line, another one from the other side touching the line here. Once we identify this support vector, new samples can easily be identified as the case may be. Now, so we said that a support vector machine is a discriminative classifier. I've mentioned that. Discriminative, which takes in training data that is done in supervised learning, and the algorithm will output an optimal hyperplane, which categorizes new examples. That optimal hyperplane separates your classes. So when we have new classes, if you fall to this side, we only need to check which side of the support vectors are you. If you're on the support vectors side of class B, you know that you belong to class B. Otherwise, you are going to belong to class A. So basically, we say that the goal of support vector machine is to find the optimal separating hyperplane, which maximizes the margin of the training data. Let's pay attention to this. The goal of SVM is to find the optimal separating hyperplane. Optimal, because there are going to be many possibilities of separating hyperplane. I can draw my line this way. You can draw your line like this. Someone might decide to draw his own like this. So you need to select the optimal, the best separating hyperplane that will maximize the margin of the training data set. That is, it's not just any margin, but the maximum margin that is possible that can separate the data set clearly. So this is what we are talking about. To say this is an hyperplane. You can see this is another hyperplane. You can see here. You can see that this line is a little bit very much upright. This is a little bit slanting. The same data. So I might disagree. I might have my own like this. I might have another. My own might be like this actually. You see, this is my own separating hyperplane. Someone might decide to say no. My own is like this. So we have a lot of possibility. So, but we have to come up with the optimal one that can separate the data in a better way. So this is the general philosophy of SVM. It always believes that no matter how your data is, we can always draw a separating hyperplane, or let's call it separating line. But we can always draw a separating line between the two classes. However, so this is going to call, this is a small margin. You can see here, we're able to, this line is good, it's separating. However, we call it a small margin. You can see, we cannot compare with large margin. You can see here. So you draw a line that, if I draw the line here, this is what has been done here. You can see that the possibility that the line is going to be larger is higher than this one, because I made it to be very, very much perpendicular here. So we have to look for the line that can produce the large margin. The same data point, the same positioning. But because the line here is chosen this way, you can see we keep pushing back. When I draw this line, this is the starting point. When you draw this line, now you try to increase this line back gradually until it touches the first data sample, which we call support vector for this side. This is support vector. You keep to the other side also, you keep pushing it back until it touches the first one and you stop. But if I draw it this way, in this slant manner, I can move it even further away before it touches anyone. At this point, it's touching this guy and touching this guy. 2 support vectors from this side, and I think 2 also from this side. This is the idea, this general philosophy behind support vector machine, that you can always draw a separating hyperplane with maximum margin between 2 classes. However, this is an assumption that the data is separable. So like I've explained, these are called the support vectors. Once you get your support vectors, we can as well do away with these other samples. In fact, it has been proven that if we keep this support vector and retrain the sample, the system with only the support vectors, they will arrive at the same answer, finally. And that is how unique the support vector is. So if we're able to get the optimal separated hyperplane, then you are good to ensure that you might get better results. So these are the support vectors, those ones that are touching the hyperplane from both sides of the classes. Now, then in the general philosophy of support vector machine, let me clarify for all, there are 2 unique cases we can have. 2 unique cases, linear and non-linear. This is the natural. Every problem we face in the world is either linear or non-linear. However, sometimes we might not know the actual type of problem that the system has. Is it linear or non-linear? Until we really check and see, is it this one linear or non-linear? However, support vector machine has that unique capability. If it is linear, it's very easy. Look at this example now. Data set that are linearly separable, they work out great. This is data set. You can see this. You can see this class in red. This is one class. This is another class. You can see in blue another class. You can see here one is on the right side, one is on the left side. I can draw an hyperplane here, draw a line, try to increase the line, gradually go back, until you touch the first sample here. So this is going to be the support vector for this problem. This is the support vector for this problem. So we have successfully drawn, this is the hyperplane, the maximum margin from here to here. Once we know the support vector, if we plot a new sample, if we fall to this side, we just need to know which side of the support vector. Is it to the side of this support vector or to the side of this support vector? We know that this new sample belongs to this side or belongs to the other class. This is the unique way it works. However, this is linearly separable. This is a problem that is linearly separable as the case may be. However, in real life, let's say, for example, I want to determine if I have a set of students in my class. I want to determine who is tall and who is not tall. Who is tall and who is not tall. This is a case of linearly separable case. This is a problem. This problem is linearly separable. I just need to ask the student to stand up. And I have my own measure. Maybe if anybody that is 5.5 and above meter, maybe it's tall, or as the case may be, or 4 and above. We have a threshold. I just say stand up, even without any measurement. When you see students in your class, ask them to stand up. You can pinpoint that, hey, sit down. You are tall, come here. You are not tall, come here. There's not going to be any issue. This is called linearly separable case. Linearly separable. Problem that can be easily solved. By just looking at it, you can solve the problem. This is the same way here. We can draw an hyperplane, a separating hyperplane between these two sets of data without any problem. However, when we go to the second case, we said, but if the data set is too hard, this is non-linearly separable. We say this is non-linearly separable case. That is, the data is hard. Look at this one. This is blue classes. You can see the blue class here. And then you can see the red class. Okay, this is, let's say the red class is class B. You can see another red class here. This is class B again. You can see, and then the class A has been sandwiched in between the two groups of class B. These are all class B, these are all class B, this is class A. How do you draw a single line between these two classes? This is not possible. This is what we call non-linearly separable case. Non-linearly separable. And in real life, I give an example that we can visualize. Let's say you have a set of students, as I've earlier mentioned. This time around, I'm not trying to decide if a student is tall or is not tall, but rather, I want to determine if a particular student can run a marathon race. Can you run a marathon race or not? We all agree that I cannot just ask the student to sit down and I look at their shape and I look at their length of body and I say, hey, you come here, you cannot run a marathon. You go here, you can run a marathon. It doesn't work that way. In fact, maybe somebody among the students, I want to sue you to court that you are saying I cannot run a race by just looking at my shape. Are you discriminating against me based on my shape? Or things like that can come up. We call this problem non-linearly separable case. And it do happen in our data set also. So how do we solve such a problem? In real life, what I will do is I will ask my students, because I want to determine who can run a marathon race, I will give them a simple task. I say, okay, everybody run from my office to the office of the president of the university and run back. Whosoever return within so number of minutes, I will classify them as, yes, you can participate in the marathon. If you come very late or you are tired when you came, or maybe you even needed an ambulance to complete the race, then even you yourself, you know that, yes, I couldn't make the list of marathon people. This is how I'm able to separate them by subjecting them to something to test their endurance that will actually facilitate my classifying them finally. This is what support vector machine come with what we call kernel trick. Kernel trick. The support vector machine has a kernel trick. My whole kernel trick now is asking the student to run to the president's office and return. For sure, we'll be able to know people who can run and people cannot run. who could not even make it. So support vector machine, whenever it's faced with this kind of situation, this is a non-linearly separable or hard problem. What does it do? It will map it to higher dimensional space. This is a very general summary of support vector machine philosophy. It will map it to higher dimensional space. How does it do that? This same data set, just look at what is going to happen, because we have problem separating it with a line. If we draw a line here, there will be red and blue here. We have not done the work. If we draw a line here, we have not done the work. Rather, so support vector machine says, you can, just like I asked my student to run a race so that I can separate them to who can run, who cannot run, it also will subject the data into higher dimension. This data, as you can see, is on one plane, X only, X axis. Now, I'll push it to second dimensional space, 2D, by generating the Y axis for this data. So the same data was here before. Now I've generated Y, I created Y, and I see my Y is X squared. What I've just done here is, each of this number here, I'll scale them. Maybe this is 1. When you scale 1, you get a 1. You scale 2, it goes up. As you are scaling them, those iron value will be jumping up here. In the negative side also, as you are scaling them, the higher value here will also be jumping up. At the end of the day, you can see that I'm able to separate this data by a line. You can see the line now. We have been able to draw a margin, the same data set. But here we could not draw a single line to separate them. But when we push the data to higher dimension, which in this case is 2 dimension, then it became separable. Now we can draw a line. Look at the hyperplane we are looking for. This is what we did here easily. But here we couldn't do it. So we had to employ the kernel trick by using the available kernel function. Once you bring in the kernel function, then it can change your data from being non-separable here to becoming separable. So this is the line we are looking for. This is the line, and this is the, you want to get the maximum margin, so you put it back. While pushing back, it touches this. This is support vector here. This one support vector. This one touches here. This is another support vector. So 2 support vectors from this side, 1 from this side. With those support vectors, we are done with our training. Then we can do classification based on those support vectors. So this is how support vector machine is able to solve any problem, either linearly separable or non-linearly separable. However, it is believed in support vector machine philosophy that even at 2 dimensions, I'm going to show you later on another example of, in some situations, you might not be able to even separate it at second level, second dimension. You push it to 3 dimension again. Remember, 3 dimension problem. If it's not separable at 1 dimension, it's not separable at second dimension, it will become separable at 3rd dimension. If not yet separable at 3rd dimensional level, keep going to 4th, 5th as much as possible. The belief of support vector machine is that at a particular appropriate higher dimension, the data set will become separable. This is a unique summary of some of the background information about support vector machine, in which case 2 unique cases can be treated, linearly separable and non-linearly separable. If it is linearly separable, it becomes very easy. Just draw the separating hyperplane immediately. However, in hard cases whereby it is not linearly separable, that's fine. We push it to higher dimension where it will become very highly separable, as we are going to see. Even sometimes we might have to go to even further higher dimensions where the system will become highly separable. However, the idea of support vector machine is every data set has its own day. If you push it appropriately to the appropriate dimension, it will get it separated appropriately, as the case may be. But if you are yet to get to the appropriate level, then it might be showing the sign that, oh, it's not yet separable. it means that you are yet to get to where you are supposed to get it separated, as the case may be. You see, this is another example of, you can see here, this data set is not separable by a line. We are not talking of a curly line. No, you must use a straight line. You cannot draw a line on this data to separate. But when we put it on kernel function, it becomes like this. You can see we can draw a line. So every data sample has its own kernel function. Sometimes it could be polynomial kernel that is going to work for you. Sometimes it's not polynomial kernel. We can see this example now. Here, look at this data sample. This is 2 dimension. The blue classes are surrounding the red classes. There's no way you can draw a line to separate them. When we push it to 3 dimension, you can see what happened. Now we can draw a line between them. Just like the example I gave, that when I ask my student to run a race between 2 buildings that are far away, we were able to separate those who can run and those who could not run. So this is the big philosophy behind support vector machine. Sometimes you have a very hard data like this, that there's no way you can draw a line between them. And machine learning, support vector machine work by drawing, separating hyperplane. So if you push it to appropriate dimensional level, it becomes separable. You can see here, it becomes separable. Others, everybody will find its level at an appropriate level. Even in real life, when you have competition among people, you keep subjecting them to competition. People will be dropping along the way. They'll be dropping along the way. So at a particular point in time, everybody gets separated. So this is the unique philosophy behind support vector machine, that if you keep pushing your data set using the kernel function to higher dimensional space, at the appropriate time, the data will become separable. I believe this is a very good place to call it a day here. So we're going to take a couple of clarifying questions, and we are going to continue from there, inshallah, next time to clarify more points about support vector machine and how we can use it and benefit from it, especially when the data set is very few. It has always worked where other machine learning algorithms failed. Thank you very much for listening, and we are going to give room for a couple of questions before we call it a day. Thank you.